Uncover the profound core of what you need to know. Today, we're plunging into what many physicists consider the greatest unsolved problem in physics. It's this fundamental, really unsettling conflict between Albert Einstein's general theory of relativity and the, frankly, perplexing world of quantum mechanics.
Hmm.
So on one side, you have general relativity, GR. It's just this sublime geometric description of gravity. It beautifully explains it not as a force, but as the curvature of this continuous four-dimensional fabric,
Yeah.
spacetime.
Right, think of it like the cosmic dance floor, where galaxies twirl in these elegant arcs.
Exactly. And then reigning supreme in the microscopic realm, we have quantum mechanics, QM.
And this theory describes a universe of discrete quanta where events are inherently probabilistic and subatomic particles exist in this fuzzy, uncertain state.
But the core tension, and this is key, is that QM traditionally assumes a fixed passive background for spacetime.
And that's precisely where the problem lies, isn't it?
Yeah. GR tells us spacetime is dynamic, it curves, it flows. QM, on the other hand, kind of treats it like a rigid, unchanging stage where quantum stuff happens.
This fundamental incompatibility, well, it's usually okay at our everyday scales. You don't really notice it.
But it becomes this unavoidable, screaming conflict at the most extreme scales.
Yeah.
Think inside a black hole, or right at the very beginning, the Big Bang.
Absolutely. And the stalemate, it's been going for over a century now. It's ignited this relentless global search for a unified theory of quantum gravity.
We desperately need a single coherent framework, something that can hold both that majestic cosmic dance of galaxies and the quantum fuzz of subatomic particles.
Right. We need the bridge.
And that search brings us to our focus today. We're going to explore a really fascinating, though, let's be clear, speculative framework known as the quantum vibrational universe, or QVU hypothesis.
It's a bold attempt to build that very bridge. And it proposes a pretty radical idea that space-time isn't this fundamental container we think it is.
But instead, it emerges from relationships and interactions. Is that right?
Exactly. The real aha moment, if QVU holds water, is that location itself isn't some fixed coordinate. It's a property of how similar one vibration is to another.
Wow. So a fundamentally relational universe where distance is born from resonance.
That's the idea. It's quite a leap.
Okay, so to really appreciate the ambition here, we should probably ground ourselves first in the physics we do understand. Start with Einstein's incredible insights into gravity.
Definitely.
Then maybe we can explore some of the leading-edge theories that are also trying to unify gravity with quantum mechanics.
Good plan. See what else is out there.
And finally, we'll really dig into, deconstruct and analyze the QVU hypothesis itself.
Okay. So to understand the challenge, the sheer difficulty of unifying these theories, we absolutely need to appreciate the genius of Einstein's general relativity first. It really all began with his foundational insight, the principle of equivalence.
Okay, this is where the famous thought experiment comes in, right? The observer in a closed, windowless elevator. What was so revolutionary about that?
Precisely. Einstein realized that locally, just in your immediate vicinity, the effects of gravity are completely indistinguishable from acceleration.
Okay.
Imagine that elevator. If it's sitting still on Earth, you drop a ball, it falls to the floor. Simple.
Right, gravity.
Now take that same elevator out into deep space, far from any gravity, but accelerate it upwards at exactly 9.8 meters per second squared Earth's gravity. A dropped ball inside will appear to do the exact same thing, fall to the floor. You couldn't tell the difference from inside.
Wow. Okay.
So this perfect equivalence between gravitational mass, how strongly gravity pulls, and inertial mass, how much an object resists acceleration, that led Einstein to conclude gravity isn't a force like electromagnetism.
Geometry.
It's a manifestation of the geometry of space-time. Objects aren't being pulled, they're simply following the straightest possible paths, called geodesics, through a curved landscape.
That's brilliant. So instead of a pole, it's about the very shape of space and time itself.
Exactly.
And he formalized this geometric vision with his Einstein field equations. I love John Wheeler's little aphorism for this. Matter tells space-time how to curve, and space-time tells matter how to move.
It's such a great summary, isn't it? Makes a complex set of equations sound almost intuitive.
It really does.
And what's fascinating here is how beautifully simple yet profound that relationship is. On one side of the equations, you have the geometry of space-time, its curvature, its structure.
Right.
On the other side, you have the distribution of all mass, energy, momentum, pressure, everything within that space-time.
And they talk to each other.
They dictate this dynamic, interactive relationship. Matter warps space-time, and that warped space-time dictates how matter moves. It was a total departure from Newton's static, absolute space and time.
A complete paradigm shift. And these observational proofs, the pillars supporting GR, they're just astonishing when you list them out.
They really are.
Like, take how GR explained planetary orbits as those geodesics, those straightest possible paths in curved spacetime. It's that classic image, the bowling ball on a stretched rubber sheet making a dip.
And the marble rolls around it following the curve, yeah.
And it perfectly explained Mercury's weird orbital anomaly that Newtonian gravity couldn't
quite nail down, exactly. It was one of the first big wins for GR.
Then there's gravitational lensing, the bending of light by massive objects.
Right. Famously confirmed by Sir Arthur Eddington back in 1919 during a solar eclipse. He saw starlight bending as it passed near the sun, just as Einstein predicted.
And now it's a vital astronomical tool, isn't it? Creating things like Einstein crosses or Einstein rings.
Absolutely. Massive galaxy clusters act like cosmic magnifying glasses. They let us see incredibly distant, otherwise invisible galaxies behind them. It's amazing.
Gravitational time dilation always gets me the idea that clocks in stronger gravity tick slower. And we're talking about time itself here, right? Not just the clock mechanism.
That's the crux of it. It's not a mechanical flaw. It's space-time itself warping, and time is fundamentally part of that fabric. It slows down in stronger gravity.
And it's real enough to affect GPS.
Oh, absolutely critical. GPS satellites are in orbit, experiencing weaker gravity than us down here on Earth, so their clocks actually run slightly faster.
Wow.
Without constantly correcting for this relativistic effect, your GPS navigation would be off by kilometers within a day. It has real-world consequences.
Incredible. And speaking of extreme gravity, black holes. GR predicted them.
Regions where gravity is so intense that nothing, not even light, can escape. For decades, they were mostly mathematical possibilities, almost sci-fi.
But then, 2019, the Event Horizon Telescope image of the M87 supermassive black hole.
Stunning visual confirmation. Seeing the shadow of the event horizon itself, it was a landmark moment for physics.
In the final, incredible piece, gravitational waves.
Ripples in space-time itself, like waves on a pond, but the pond is space-time, generated by accelerating masses, especially extreme events like merging black holes or neutron stars.
And the 2015 LIGO detection from merging black holes.
Yeah.
That wasn't just proof, right? It was like opening a new sense.
Exactly. It opened a whole new window onto the universe. We can now hear cosmic cataclysms through these space-time vibrations. It's a completely new kind of astronomy.
So the key takeaway here before we move on is just how comprehensive and geometric GR is.
Its triumph is its geometric nature, and every prediction flowing from that foundation has been rigorously tested and verified.
Which means any new theory, including this QVU idea we're looking at,
has a very high bar to clear. It must, at the very least, reproduce all these established, verified predictions. It needs to match GR where GR is known to be right, and somehow incorporate quantum mechanics where GR breaks down.
a tall order. Okay, so we've established GR's dominance for the cosmos, the gold standard for gravity on large scales. But as we said at the start, it hits that wall at the quantum level. That fundamental conflict is what's driving physicists on this quest for a unified quantum gravity theory.
The holy grail, really.
So let's look at the leading contenders trying to bridge that divide. Because they approach the problem from really different philosophical and mathematical starting points, don't they?
Absolutely. They come at it from different angles. One of the most prominent, maybe the most famous, is string theory, often called a theory of everything because of its, well, ambitious scope.
Right. And its core idea is swapping point particles, those little dimensionless dots, for tiny one-dimensional vibrating strings.
Exactly. Instead of a point, the fundamental constituents of reality are these minuscule vibrating filaments, either loops or open segments.
And different vibrations mean different particles.
Yeah.
Like how a single violin string makes different notes.
That's an excellent analogy. The different vibrational modes, the different ways a string can wiggle, correspond to all the different particles we observe, electrons, quarks, photons, everything.
So it's unifying in that sense.
Very much so. It has this inherent elegance, one fundamental object giving rise to all the diversity. And what's truly remarkable is that gravity isn't something you have to put in by hand.
It just pops out.
It emerges naturally. One specific vibrational mode of a closed string has exactly the properties massless, spin 2 of the hypothetical graviton, the quantum particle that should mediate gravity.
That's pretty compelling. But string theory has its hurdles, right? Like needing extra spatial dimensions.
It does. Typically 10 or 11 spacetime dimensions in total. The idea is the extra ones are curled up or compactified, incredibly tiny, so we don't perceive them directly.
Hmm. And the landscape problem, I've heard about that.
Yes, that's another challenge. String theory seems to allow for a vast number, maybe 10 to the power of 500 of possible vacuum states, each corresponding to a different universe with potentially different physical laws. Why our universe? That's a big question.
Okay, so that's string theory. What's another major approach?
Loop quantum gravity, or LQG. This takes a fundamentally different path. It's what's called background independence.
Meaning it doesn't assume space-time is a fixed stage.
Exactly. String theory often starts with a background spacetime and puts strings in it. LQG tries to build spacetime itself from quantum principles. It quantizes geometry.
Whoa. So space-time itself comes in chunks. Like at the Planck scale, that unimaginably tiny 1035 meters, it's not smooth.
That's the picture. LQG describes spacetime at that scale as a discrete, foam-like structure made of spin networks, basically graphs with quantum information on their nodes and links.
So properties like area and volume aren't continuous, they're quantized. There's a smallest possible area, a smallest possible volume.
Precisely. A minimum quantum of space itself. It's a granular spacetime, no smooth continuum at the bottom.
Okay, radically different from strings. Are there others?
There are even more radical ideas, often grouped under emergent gravity or the holographic principle.
Right, you mentioned Eric Verlinde's idea, entropic gravity.
Yes, the idea that gravity isn't fundamental at all, but an entropic force, something that arises from information and the universe's tendency towards disorder, linking gravity to thermodynamics.
That's a wild connection, and the holographic principle.
Also mind-bending. The idea that all the information contained within a volume of space can actually be encoded on its boundary, like a hologram. It suggests our 3D reality might be a projection from a lower dimensional surface.
Makes my head hurt just thinking about it.
And related to this is the idea that space-time and gravity might emerge directly from patterns of quantum entanglement between fundamental quantum bits or qubits.
So the geometry of space is literally a map of how entangled things are.
That's the direction some research is heading. Space-time from entanglement. It's a very active area.
Okay, so if we bring this back to the QVU, the quantum vibrational universe,
Yeah.
it sounds like it's trying to be a bit of a mix and match.
In a way. It seems to borrow the hardware, if you like, from string theory, the idea that everything is fundamentally vibration.
Right.
But it builds its space-time using software, more akin to emergent gravity, making it relational, dependent on similarity, background independent in spirit.
So it's this creative, ambitious hybrid, which definitely sets the stage for asking, okay, how viable is this QVU hypothesis? Let's dig into its core ideas.
All right, let's deconstruct its three main postulates. Postulate 1. Everything is composed of vibrations of ever finer degrees.
Okay, straight away that word finer. What does that actually mean? Is it higher frequency, more complexity, a different kind of vibration altogether?
That's the immediate question, isn't it? It's quite qualitative. Unlike string theory, where you have one fundamental string and its harmonics give you particles, QVU doesn't clearly state the organizing principle behind these finer degrees.
So there's a risk it just becomes this, I think you called it chaotic soup of vibrations. How do stable structures like particles or atoms emerge?
Exactly. Finer degrees needs a much more precise mathematical or physical definition to be workable, to explain stability and structure.
Okay, what's the second postulate?
This one is perhaps the most novel and the most radical. As the vibration of an object gets closer to the vibration of another object, they become closer in spacetime.
Whoa, okay, unpack that. Location isn't XYZ coordinates, it's how similar my vibration is to yours.
That's the essence of it. Distance isn't fundamental, it's derived from vibrational similarity. Closeness in vibration space translates to closeness in physical space.
So this implies there must be some kind of mathematical vibration space, right? And a way to measure distance or similarity within that space.
Precisely. You'd need to define this abstract space and a mathematical function, a metric on it. And crucially, this metric, based on vibrational similarity, would somehow have to reproduce the geometry of our familiar 3 spatial dimensions plus 1 time dimension.
That sounds incredibly challenging. Does it connect to anything else in physics?
Well, conceptually, it echoes those ideas in emergent gravity, where quantum entanglement defines geometric distance. The more entangled two quantum systems are, the closer they are in the emergent geometry. QVU needs to show how vibrational similarity could play a similar mathematical role.
Okay. And the third postulate, the mechanism of gravity.
Postulate 3. Massive objects emanate a spherical vibration, and other objects alter their course trajectory to match this spherical shape.
Hmm. Emanate a spherical vibration. Sounds a bit like an Oldfield idea.
Yeah.
And match this spherical shape. How does that connect to GR's curved spacetime?
It does sound a bit pre-relativistic, doesn't it? A more generous reading might interpret the spherical vibration as a simplified way of talking about the spherically symmetric gravitational field, or spacetime curvature, around a massive object like a star or planet.
Wow.
And altering trajectory to match could be a non-technical way of saying following a geodesic in that curved spacetime.
But doesn't that raise a problem if the object itself is already a vibration according to postulate 1?
Exactly. You've hit on what we could call the two-step problem. If the massive object is vibration A, why does it need to create a secondary vibration B, the spherical vibration, to mediate gravity?
Yeah, what is that secondary vibration? Is it made of something else? How does it travel? It seems less elegant than GR or even string theory.
It does seem less parsimonious. In string theory, for instance, gravity is mediated by exchanging gravitons, which are just another vibrational mode of the same fundamental strings. There isn't this two-step process.
Okay, so that's the core structure. Now, the big tests. How does QVU stack up against established physics? Can it reproduce the basics, like the inverse square law of gravity?
Well, conceptually, if something emanates spherically, its intensity naturally decreases with the square of the distance just due to geometry, like light from a bulb getting dimmer further away.
So that part seems plausible, at least qualitatively.
Qualitatively, yes. But the QVU hypothesis, as it stands, doesn't provide the mathematical machinery to show how this vibrational intensity translates into the specific attractive force or spacetime curvature we observe. It needs to connect the concepts.
Right, and what about things like gravitational lensing? How does this spherical vibration bend light, given that photons are massless?
Another crucial question. The mechanism needs to explain how this emanation affects particles, whether they have mass or not.
And time dilation. How does time fit into this picture? Is time itself emerging from vibrations? How would a spherical vibration affect the rate of time?
Again, these are fundamental predictions of GR that any alternative needs to replicate. QVU doesn't yet offer quantitative explanations for them.
Then there's conservation of energy and momentum. Super fundamental.
Absolutely critical. When an object falls, say, towards Earth, its potential energy converts into kinetic energy. In QVU, this entire process, the fall, the energy change must correspond to changes in the vibrational states of the object and perhaps the Earth.
And the total energy and momentum must be conserved throughout that vibrational interaction.
Exactly. The model needs a framework, like the Lagrangian or Hamiltonian formalisms used in standard physics, to guarantee these conservation laws hold. That framework is currently missing.
And the nature of mass itself seems tricky. If mass is just the energy of a vibration, like in string theory, then why do only massive vibrations, according to postulate 3, generate this secondary spherical vibration that causes gravity? What about massless vibrations, like photons? They have energy, there are vibrations in this view, presumably, but they don't create gravity in the same way.
That's a very good point. Why the distinction? And why are massless particles, like photons, affected by this spherical vibration if they don't generate it? QVU needs a clearer explanation for the role of mass energy in generating and responding to gravity.
So it seems like there are quite a few conceptual hurdles and unanswered questions.
There are. It's important to acknowledge the QVU's primary strength, though, which is its sheer ambition for unification.
Trying to get particles, location, and gravity, all from one basic idea of vibrations.
That's the dream, the holy grail of physics. Proposing a single vibrational foundation is conceptually appealing.
But the weaknesses, the open questions, seem pretty significant at this stage.
They are. We've touched on several. The problem of time, for instance. Is time fundamental in QVU, or does it emerge? The hypothesis is silent on this, but it's a crucial structural question.
But what about the other forces? Gravity is just one of 4.
Right. How does QVU account for electromagnetism, the strong nuclear force, the weak nuclear force? Do they also arise from vibrations? Perhaps differently shaped emanations? A true theory of everything has to incorporate all known forces and particles.
And it's called the quantum vibrational universe, but where's the quantum mechanics?
That's a key point. Despite the name, it lacks an explicit quantum framework. How do core QM principles like superposition, the uncertainty principle, quantum entanglement, how do these arise naturally from a purely vibrational model?
Without that, it can't really claim to resolve the central conflict between GR and QM.
Precisely. And finally, there's the stability problem we mentioned earlier. What keeps the universe from dissolving into that chaotic soup of interacting vibrations?
Do we need something like supersymmetry, as in string theory, or the discrete structure of LQG, to impose order?
QVU currently doesn't propose any specific organizing principle or selection rule to ensure the kind of stable, structured universe we observe.
So, summing up this section, QVU feels more like a conceptual sketch, maybe relying heavily on analogies, rather than a fully fleshed out formal theory right now.
I think that's a fair assessment at this point. It's provocative and interesting, but qualitative.
Okay, so let's try to synthesize all this.
All
The
right.
QVU is undeniably creative. It's pulling threads from different, very advanced areas of physics.
It shares that vibrational core idea with string theory.
But its concept of spacetime being emergent, relational,
Uh-huh.
that feels closer in spirit to loop quantum gravity or those entanglement-based ideas.
Agreed. It's an ambitious hybrid, trying to bridge different approaches. But as we've discussed, it currently lacks the mathematical rigor and, crucially, the predictive power of its more developed rivals, like string theory or LQG.
So what would it take? What are the crucial steps needed for QVU to move from being an intriguing hypothesis to a potentially viable scientific theory?
Well, the first and perhaps biggest step is formalization, rigorously defining that vibration space.
Right. Mathematically pinning down what exactly a vibration is in this context, and then defining that distance function, the metric based on similarity, and showing it can actually reproduce 3 plus 1 dimensional space-time geometry. That sounds like a monumental task.
It is, and alongside that, it needs to develop field dynamics.
Right.
Meaning writing down precise equations. Equations that describe how sources, massive objects, generate these vibrational fields, how those fields propagate through space or vibration space, and how they interact with other objects to produce the effects we call gravity. And these equations must match observations.
And ideally, you'd want a Lagrangian formulation, right? You mentioned that earlier.
Yes, that would be a huge step towards robustness. Finding Lagrangian, that sort of master mathematical principle, would automatically ensure things like energy and momentum conservation, which are non-negotiable in physics. It lends a lot of structure and predictive power.
And given its core idea of distance from similarity, exploring connections to information theory seems vital.
Absolutely. Since the metric is supposedly information-based similarity, exploring how concepts like quantum information, maybe entropy, or particularly quantum entanglement, could provide the necessary mathematical tools seems like a very promising direction. Could entanglement be the measure of vibrational similarity that builds geometry? That's a question worth pursuing.
So it's a fascinating concept, but with a long road ahead if it's to become a serious contender.
A very long road, requiring significant mathematical development and eventually testable predictions that differ from standard theories.
Right. Well, the quantum vibrational universe hypothesis, even in its current state, is really a testament to the power of speculative thinking in physics, isn't it?
It is. These kinds of what-if questions, even if they don't pan out, force us to push boundaries.
They make us re-examine our deepest assumptions about reality, about space, time, matter, and that's always valuable.
So perhaps the final thought for you, the listener, to ponder is this. Can a universe described as pure vibration, ultimately through the rigorous logic of mathematics and the demanding tests of experiment, give rise to the smooth geometric grandeur of Einstein's cosmos and the strange rules of the quantum world?
That is the profound question, really, at the heart of this whole quest for a unified theory. It's what keeps physicists searching.